Welcome to Unit 2. The focus of our unit here, after building all of our chemistry skills in Unit 1, is to look at how all these compounds and elements that we've studied interact with each other via some very predictable patterns. Before we get into sort of the notion of what these families and these patterns might be, though, we're going to go back and do a little bit of review from grade 10 to make sure that you have some essential skills before we move on. So the focus of this first review video, video 1A, is to look at the difference between physical and chemical changes and also introduce you to how to convert from word equations into chemical equations. So let's do a very quick review of what the signs of a chemical change are. So when you put two substances together, how do you know by looking at them that they are undergoing a chemical change? Well, one of the ways is that you sometimes observe a change in color, and not just intensity from darker to lighter, but a complete color change. You might also see the formation of something called a precipitate or a solid. I like to nickname them funky chunkies. And the solid forms when there's no energy change associated with that reaction. So you're not heating it up or cooling it down. So it seems pretty abnormal that you can take two things that might be in aqueous form or might be in liquid form, mix them together, and all of a sudden a solid appears out of nowhere. That's the kind of thing that I'm talking about here when I talk about formation of a solid. You can also see formation of bubbles. In other words, a gas is being produced, and that there's a minimal energy change associated with the formation of those bubbles, so they're happening just at room temperature. So this is not like taking water and getting it to a roaring boil on a stove and seeing, woo, bubbles. That's not an example of a chemical change. This is the result of a new substance being produced, so not just water vapor in the case of our boiling example, but some other type of gas. And oftentimes energy can be given off as heat or light. Sometimes energy can be taken in too, and the substance can get colder, like what goes on in some chemical ice packs, although some are chemical based, some are physically based. But more often we see, we think of explosions or combustions, and lots of heat and energy given off is a good sign of a chemical change. We do have to be careful with this one though, because energy changes are actually a crucial part of what physical changes are as well. So chemical changes often have to have one of the first three, and the last one there, the fourth one, can be in conjunction with those first three. But the fourth one, just in and of itself, you have to be a little bit cautious of. So physical changes in matter include one of the obvious ones, which are changes of state. So interchanging between the solid state, the liquid state, and the gas state. And that's a result of either adding energy to that system or taking energy out of it. But the substance is the same before and after. So think of water going from ice through to being a liquid through to being water vapor. Dissolving a substance in water is also a physical change. Think about adding salt to water. It dissolves and it seems to disappear, but it's still salt and water, and you can still get the salt back if you evaporated the water off. When a substance is dissolved in water, we call it the aqueous state. Aqua, meaning water, means it's dissolved in that substance. And then finally, the other thing we can do to matter, which is considered to be a physical change, is we can decrease its particle size. So we could take, a large crystal of salt and we could crush it, or we could, take a piece of paper and cut it up. We could take, a piece of sodium and cut a little piece off to use for a reaction demonstration. We haven't changed the substance in any way in terms of its composition. We've just made its particle size smaller. And so those are examples of chemical changes and physical changes. Now, throughout all of these changes, the law of conservation of mass says that matter is not gained or lost throughout these changes. So we can't just magically create matter, and we can't just magically have matter disappear. That it will be there before and afterwards. The next skill set I'd like to focus on in this video is converting from word equations to chemical equations. And so I'd like to go through 3 examples with you to show how this process works. This is taking the skill set that we have learned about in Unit 1 and just bumping it up a little bit to incorporate reactants and products. So one of the first things I like to do when I'm going from a word equation to a chemical equation is I like to block it out into ways that I can substitute words with specific symbols. So the first thing I see in A is the word sodium, and then it says reacts with. So sodium here is all by itself, and so I'm going to block it out just like that. Reacts with means it combines with, or it must be added to another reactant, and that next reactant is listed. It's called chlorine. And then to produce is a clue that there's a change going on, a chemical change, in that we're no longer just examining the reactants, but they are breaking apart and recombining to make something new. So I'm going to block off to produce, and then I see that sodium chloride combined together is the name of a compound, and so I'm going to block it off as well and replace it with its chemical formula. So going through piece by piece, sodium by and of itself is just meaning elemental sodium. Elemental sodium is neutral, and because it's a metal in the periodic table, we know that it's a solid at room temperature. The only metal that's not, of course, is mercury. Reacts with just means that there's another reactant being added, and the next one then is chlorine. And our instinct might be just to write Cl, but we do have to remember that chlorine is a member of the Hofbrinkel family. And Hofbrinkel is that acronym that we use to help remember that there are 7 elements that exist as partners of themselves when they are elements, not when they're in compounds, but just in their elemental state. So chlorine is one of them. It's the last part of Brinkel, and so we must write a 2. And at room temperature, we can use our periodic table to see what state of matter it is, and we would discover that it is in fact a gas. And so we can show that using a subscript G. To produce can be replaced with an arrow. And then sodium chloride. So this is naming an anionic compound, and I know it's ionic because I have a metal with a nonmetal. So sodium in this case is going to be Na1+. It's going to be ionic sodium because it's combining with chloride, which I know is Cl1- from my periodic table. And when I put those two together, I notice that they combine in a 1-to-1 ratio because their charges are equal. Now, sodium chloride is an ionic substance, and when these two combine, ionic substances, of course, at room temperature are always solids. And since there's no water present, or it doesn't talk about dissolving this salt in water, we would put that it's in the solid state. Our next step is to go back and balance the equation. So when I look at left side and right side, I see that the sodiums are balanced. There's one of each type of sodium. But on the left side, there are 2 chlorine atoms, and on the right side, there's a chloride, okay, 2 Cls. On the left, 1 on the right. So to fix that, I'm going to put a 2 in front of sodium chloride like this. That's going to give me 2 Cls, but it's also going to give me 2 sodiums. So I need to go back to the left side and say, let's make sure there's 2 sodiums there, and then the equation is balanced. Let's do another example. Again, let's begin by reading it through once and then chunking it so that we can take each chunk and represent it with a different type of symbolage. So the first thing says copper metal and aqueous sulfuric acid or hydrogen sulfate react to form a solution of copper 2 sulfate, and sorry, this should say hydrogen gas. It's a typo. Let's fix that. There we go. Okay. Copper metal is the first piece, and aqueous sulfuric acid. Now I've chosen to put here both sulfuric acid and hydrogen sulfate. Sulfuric acid for the 3 U's, hydrogen sulfate for the 4 C's. It is actually one substance. I've just given it both of its names. And the word aqueous is a hint in there too that we'll know what state of matter it is. React to form means we're now going from reactants into products. And so we're going to go from left side of the equation to right side. And then a solution of copper sulfate and hydrogen gas. All right, let's replace these one at a time. So copper metal is just elemental copper. And copper metal would be a solid at room temperature well because metals are solids except for mercury, as I said earlier. And would be a plus sign. Hydrogen sulfate or sulfuric acid. Hydrogen sulfate is a really nice way to look at the name because it tells you that it's an ionic compound, and we would have H plus combining with SO4 2 minus. And you could look those up in your Alchem table. Problem we run into here though is that the 1 plus of hydrogen and the 2 minus of sulfate don't match. So in order to make them match, we require 2 H pluses so that they are neutral overall. And then in the question it says aqueous, so we can put AQ. So it means that hydrogen sulfate has been dissolved in water before it's being used as a reactant in this equation. React to form, communicated by an arrow, so to the right to show there's a transformation from left to right. A solution of copper 2 sulfate. Well, copper 2 means I have this combining with sulfate, which I have from the left-hand side. Good news here is they combine in a 1-to-1 ratio charge-wise. And because it says a solution of again is just another word or phrase for saying dissolved in water. So I can put AQ here. And hydrogen gas. And again, our instinct might just be to do H with a G. But again, we have to be aware that hydrogen is one of those 7 elements that exists as a diatomic when it's just out by itself in its elemental state. And here it is. It's not combined with anything else. So I will put in H2 here. Now the wonderful thing about this equation, if we compare left side and right side in terms of types of elements present, is it is in fact balanced. We have 1 copper on the left, 1 copper on the right, 2 hydrogens here, 2 hydrogens here, an sulfate or an S and an O4 here, and a sulfate, an S and an O4 here. So no further balancing is required. I invite you to pause the video at this point and see if you can break down word equation C, take the time to block it out and to replace it with symbolage as required, and then unpause it and see how you did. Okay, compare your answers with mine. We have crystalline glucose. And you're given the formula for crystalline glucose. So crystalline just means it's a solid. And so I've indicated that down here with the letter S. Is burned in oxygen just means that oxygen is another reactant. And there it is. And again, oxygen is one of our Hofbrinkel ones to remember. When it's burned, carbon dioxide, gas, we can put that all together, is right here. And water vapor are formed. Now are formed just means that it's on the right side of the equation, which you've already got it there. And there's our water vapor, water with the gaseous symbol. So the last step for us to do is to balance the equation. If we look on the left, we see there are 6 carbons. So let's balance the right side by also creating 6 carbons, multiplying the right side by 6. We also notice that there are 12 hydrogens. So let's create 12 hydrogens on the right by also multiplying that water term by 6. Now what that does on the right hand side is it gives me 12 oxygens from this term and 6 times 1, which is 6 from this term, which is a total of 18 oxygens in total on the right hand side. So oxygen is in 2 places on the left. It's here and it's here. I don't really want to mess with this one too much because if I put anything out in front out here, I'm going to mess up the carbons and the hydrogens again. So why don't we think of it this way? I have to have 18 altogether on this side, and I've already got 6 in this one term right here. So that means that there are 12 remaining that have to be on that left-hand side. Well, the good news is we have a term right here that we could use to create the remaining 12. We could multiply this one through by 6, and we would get 12 altogether. And then the left side would be balanced with the right side. And so there you have it. The skill sets covered in this video include being able to recognize chemical changes from physical changes and knowing the difference between them, and also how to take a word equation and break it into smaller pieces and represent it using chemical notation of chemical formulas, plus signs, arrows to separate the reactants from the products, and the different states of matter that are present on both sides of the equation.